Hey, good day. Welcome. We're going to get started today talking about solving systems of equations. And so the first thing that we probably want to answer is why? Why do we want to bother to solve a system of equations? What's the point? What's the what do we get from it? What do we learn? That sort of thing. Okay. So if we start thinking about orange juice, you're all familiar with orange juice. The question I would ask you is, how much orange juice would you be willing to buy at a specific price? Okay, generally speaking, would it seem reasonable that as the price of orange juice went up, and we're moving along this axis right here, you would be willing to buy less orange juice? Sort of, like if it was free, you'd take as much of it as you could get, and if it's, say, I don't know, $100 a glass, nobody would really want any, right? So generally speaking, we might draw a line that looks like this, and we would call that line the demand for orange juice. Okay, and generally speaking, with most products, as the price goes up, the amount that people want goes down. Okay, picture yourself now as a person that's, I don't know, making orange juice, growing oranges, that sort of thing. And the question would be, how much orange juice would you make, depending on the price? Okay, so, and generally speaking, as the price of orange juice increased, you'd probably be willing to make some more, right? And no one really would want to give away. Maybe a few people would give away their orange juice. The state of Florida does, but that's only when you stop at their rest area when they come into the state. But that is a whole other story. So, generally speaking, the supply of orange juice might look like this. Okay, and so the way this whole thing works is that given that there's supply and demand and these two lines meet, right here, this would be how much you would charge for orange juice. This would be how much orange juice you would produce. So where the two lines cross would be where what people want meets what people are willing to buy. Okay, so that's called the equilibrium price, and that's largely how prices are determined in a fixed market or something along those lines. But generally speaking, so let's just say suddenly it came out and it was discovered that orange juice was the cure-all for all disease. If you drank a glass of orange juice every day, um, you'd never get sick of anything. You'd live forever, okay, or a reasonable amount of time. So what would generally happen if that was the case is more people would want orange juice. So you'd see this line move. Oh, see this line move, right? And so if this line moves because more people are willing to buy more orange juice, no matter what the price is, generally speaking, what's going to happen is the price of orange juice is going to go up because now they're crossing in a different place. People are going to be willing to make more, that sort of thing. Going back to where we were, if suddenly there's a crop freeze in Florida, okay, and there's less orange juice available, there's less oranges because the oranges all freeze, what's going to happen is there's going to be less orange juice available at any price, and what happens? The price goes up. Okay, so the system of equation stuff is actually used in economics to sort of determine prices of things. If you watch how prices go, you'll see that that's what happens whenever there's any kind of controversy. Okay, we have three ways that we can solve systems of equation. The one we worked on in class today was called graphing, and so we just graph the two lines and away we go. We can also solve it using a table, and lastly we can solve using algebra. I'm not going to go back through the graphing because we did that extensively today. You just graph the two lines and you look for where they cross, and that is your answer. If we go to a table sort of model, okay, I'm going to actually go right to the calculator. These are my two equations that I would want to find out. I want to find out where these two intersect. Okay, I've set the windows up. If I look at the graph, okay, there's the graph. I think there's the graph. Here it is. Come on, there it is. Here's the graph over here. We can see where they intersect. We could probably count up. The other way we can do this is we can go to a table, and I probably need to reset my table so it looks nice. I would set the table so that it starts at 0 is fine, counting by 1, and I need to make this in that mode. So when I go to table, and we just get to table by second graph, right above graph is the word table, then what we do is we look down the y values until we find two y values that are the same in both of my rules. 5 and 40 aren't the same. Oh, look, right here. They're both 20. Okay, so that means my two y's are equal, okay, which is what we're looking for, my two y's to be equal, and that happens when x is 5. Okay, so if I go back here, we would look for the place, let's highlight, we would look for the place where, there we go, almost right there. See, we get the two, very nicely fixed. The two y's are both 20, so when you get the same y value in both of your rules, you read over and the x value is there, so we would say that the solution to this, let's go to the pen now, the solution to this is that x equals 5 and y equals 20. So we can easily set up a calculator, put the equations into the y editor, and just go to the tables, and we can find that value. Okay, it's nice if it's a whole number. It's all nice and good when they get to be not whole numbers. The table's not as useful. Okay, so that covers that way. The other way is what we call algebra. Okay, and we refer to this method sometimes as the setting equal method. Okay, because what we're looking for is we're looking for the y values to be the same. So we want to know where this y is the same as that y. That's what we just did on the other table, right? So since these two y's have to equal each other, we say that what the y's are equal to have to equal each other. Okay? 5x minus 3 equals 2x plus 6. We just take this part and make it equal to that part, because they're both equal to y, and y should be the same thing. So we've done this problem before. We've solved equations where we have variables on one side, and the method is, remember the letters on one side, and the numbers on the other. That's our way that we go about doing this. Numbers on the other. Okay? And so, I don't know, let's probably get rid of this 2x. That seem reasonable? Subtract 2x from both sides. 3x minus 3 equals 6. And from here, it's a jolly hand clapper. We know how to solve these really easily. I think we add 3 to both sides, right? 3x, 6 plus 3 used to be 9. Divide by 3, divide by 3, x equals 3. Yay. All right, so we're not done because we need to know what y is in this case. So the way to figure out what y is, we just plug x into one of our equations up here. Okay, so let me grab a different color just so we see we're doing a different step. So y is equal to 2 times x, which we know is 3, plus 6. I just used this equation, the red one I'm circling in red. 2 times 3 is 6. 6 plus 6 is 12. So y equals 12. So when we're solving these systems of equations, we need an x answer, we need a y answer, and there they be. X equals 3, y equals 12. All right? I will leave this one for you to do. Okay? The basic thing is we're going to set them equal to each other. So we're going to start with 4x minus 3 equals 5x minus 6. I'm going to just move forward and let you do that one and show me tomorrow in class. And then we'll move on to our little story problem. Okay? So you can do this. Letters on one side, numbers on the other. Show me what you know. All right, and then the typical sort of problem where we might run into this situation is some sort of thing where we're comparing two things. A lot of times we compare phone companies. You might compare your cell phone plan. You might compare lots of different things. Today, we're going to compare pizzas. So the situation is that a pizza at Steeples is $8, small cheese, and when you get extra toppings, it's 75 cents an extra topping. So depending on what you like on your pizza, it costs you more than $8. Now at Nan's, a small pizza costs $6. Okay, but the additional toppings are $1.25 each, and these are just made-up numbers. Please don't go to Steeples or Nan's and tell them that I said you could get a pizza for this amount, or don't feel like anybody's ripping anybody off. It's just made-up math numbers. The only thing that is real is that Steeples exists and Nan's exists. So anyway, the question is, how many additional toppings would you need to order for the pizzas to be the same price at both stores? So, you know, where's that place where it's just as easy to get a pizza at Steeples, or just as cheap to get one and less expensive, whatever, at one store versus the other? So we're going to set up a couple equations, okay? We're going to set up a Steeples equation. Steeples. At Steeples, we're going to try to find out the cost. And the cost is $8 plus 0.75 per topping. That make sense? Okay, good. And at Nan's, my cost is $6 plus $1.25 per topping. Okay? So that works. And what we want is we want their cost to be the same price. Okay, so what we're going to do is that same thing that we just did on the other page. We're going to set them equal to each other. So we're going to say that the cost at, we want to know when's the cost at Steeples equal to the cost at Nance. Okay? Same story, letters on one side, numbers on the other. I'm going to probably go with subtract 6 from both sides. I'm going to go a little backwards from what I usually do, but I'm going to try to keep things with positive numbers. 8 minus 6 is 2, so I've got 2 plus 0.75 t equals 1.25 t. We'll extend a little bit further. Things get smaller as we go. Subtract 0.75 t from both sides. Okay, it doesn't matter which side they're on as long as they're together. All I have left over here is 2, and I have over here 0.5 t. So to go from that next step, we divide by 0.5, we divide by 0.5. Sorry, this is 1. So t equals 4. Okay, 2 divided by 0.5 is 4. So what that means in this situation is if you're going to get four toppings on your pizza, you can order from either place. If you're going to get less than 4, then it's probably cheaper to go to Nan's because you start out with a lower priced pizza anyway. So, at less than 4, you're better off going to Nan's. If you're going to get more than 4 more than 4 toppings on your pizza, then you want to end up with going to Steeples because it'll cost you less in the long run. Okay. Obviously you got to decide which pizza you like better, whether it's worth the extra money. But if they're exact same pizzas, taste the same, everything, all other things being equal, 4 toppings is where you switch. Okay, so if it's less than 4, we want to go to Nan's for the cheapest pizza. If it's more than 4, we want to go to Steeples for the cheapest, least expensive pizza. Okay, that's how it works. There's a way that we can use systems of equations. I've been rambling on for a while. I think I'm done. I know I'm done. That's about it. So thanks for watching. I hope you enjoyed the show, and I hope you learned something, and we'll be able to figure out how to use it tomorrow. Thanks. We'll see you then. If you have questions, of course, you know to ask. Bye now.